Right. Hi everyone. It's 9 o'clock on my watch, so I reckon we'll kick it off. Thanks everyone for joining. We'll do a couple of housekeeping things first, and then we'll jump right into it. So this module is called System Design in Heatloads. I'm Stefan. We'll run through the presentation for about 30 minutes, and then we might have up to 15 minutes in question times. What we'll do throughout the presentation is I'll keep you guys muted, and if you want to chat in the group chat, and you can either address the questions directly to me or to everyone, just as we go, if you have any questions, jot them down in the group chat. And by the end of it, once we get to the end of it, I will address them in chronological order. I reckon because we have only 30 minutes here, that's how we'll do it and how we'll keep it. We'll then head into module 2, which gives us another 15 minutes, so a total of 60 minutes. And what we'll do after the second presentation is I might actually unmute you guys if you like, and we can have a bit of a more open discussion, a bit of a back and forth to maybe clarify some more complicated concepts. Just another couple housekeeping things. On the bottom of your screen, you should see a reactions button. If I could get maybe 1 or 2 thumbs up or something, just so you guys can confirm that you can hear me, that'd be awesome. I'll see if I can see it, if I get the hang of Zoom. Perfect. That's awesome. Thanks very much. Good start. Okay, so we'll jump right into it. Half an hour is a set maximum. I might be able to crunch through it a little quicker. So what we'll do in this module is we'll look at system designs and heat loads and sizing of dwellings in general. Just as I said, first module will be relatively not superficial, but sort of level 1. And then module 2 will delve into it a little deeper, explore a couple slightly more complicated concepts maybe, and then have time to discuss all of it. All right, so I'm hoping you can see my presentation. Just to kick it off as a starting point, this is, as I said, about system design and heat loads. And you see here a quick preview of what we can achieve with a well-designed system, meaning pretty much all aspects of your home, including heating, cooling, domestic hot water, even the pool, PV, solar thermal integration. All these things are possible if the system is designed nicely and balanced well, and not over or undersized. And that's sort of, I guess, the end game of where we want to go with those 2 presentations is for you to understand what this here means. Sorry, I'm stuck. So what a schematic like this would mean, what it describes. Might be a little bit of information overload right now of the start, but by the end of at least module 2, I hope that it sort of will make sense to you. All right. So before we go into system design and schematics, let's touch on some basics, such as heat load calculations, understanding a building's performance, how to sort of read building performance reports, for example, and how to calculate the basic information that we need in order to actually size a system and pick a suitable heat pump. Now, standard building heat load basics, the heating output that must be delivered into a dwelling at the coldest outdoor temperature is what we call the design temperature. So that always describes the coldest point in whatever region you are, and is designated as the standard heat load of a building. To obtain the desired indoor temperature, which is probably around 21 at all times, the heat load must be able to be met by the heat pump's output capacity. That is relatively straightforward. Where it gets a little more interesting is that a well-designed system should not under or over-deliver too much, meaning under-delivering, meaning we don't need a secondary heat source or an element to kick in at a certain temperature. That temperature we would call bivalence point. We'll delve into that later as well. And it should also not be too large, because at that point it'll actually operate a little inefficient, because we have obviously a range for the compressor. And if that range is relatively large, but towards the lower end, it doesn't cover as much capacity, then all the compressor can do is no longer ramp down, but it would have to actually click on and off and on and off and on and off to deliver those smaller loads. And that also means inefficiency. So ideally, we find just the right heat pump to cover 80 to 90% just via the inverter ramping up and down. The output capacity of any heat pump can vary, and it will vary to a certain degree at least. What you can see, I'm sure you can see my pointer. Actually, I'm not sure, but I have a pointer here. What you'll see is that with air source heat pumps, for example, the capacity actually increases quite a lot with the outdoor temperature rising, which makes a lot of sense because it takes energy out of the ambient air. Whereas with a geothermal heat pump on the right, that output is relatively constant, and that's due to the soil temperatures being relatively constant. throughout the year, no matter whether we're in a warm season or cold season. That doesn't change. And then final sentence, maybe the standard heat load is a property of the building and forms the basis for the sizing of the heat pump and the distribution system. This is not to be confused with the annual heat demand, which is usually unsuitable for sizing the heat generator. So there's two different things. One is obviously throughout the year, 365 days, the overall kilowatt hours, for example, that we require to keep the place warm and cold. And the other one is, as I said, the design temperature heat load, meaning what is the kilowatt number that we need at the coldest time of the year to keep the place nice and cozy. All right, so with that basic established, this is what we'll do in terms of calculating heating and cooling loads. That's all we're going to do in module 1. In module 2, we'll actually delve into a couple more approaches or strategies to doing this a little more accurate. However, for heating, a relatively basic number would be anywhere between, as you can see here, maybe 50 watts per square meter up to 160 watts per square meter for conditioned area in a house. You'll see that we're most likely in Australia in the upper sort of percentile, I would say, or at least upper half, maybe down to 80 watts, meaning that the home, a newly built home now would probably have a double glazed windows, 1 to 2 stories, definitely R2.5 thermal insulation of the external wall, maybe more than that. And we're in the 80 watts sort of area, at least in Melbourne per square meter. If it gets better in Europe, we're talking half that number. We're talking 30, 20. We're talking really good numbers, and we'll slowly catch up in Australia, but we're not there yet. So relatively, so 70 to 80 watts per square meter is probably a fair bet. For cooling, we do the calculations in cubic meters. Apart from that, again, you have a rule of thumb, which is per cubic meter, watts per cubic meter would be 30 roughly for a domestic home, 40 for offices. And then when we talk like glass extensions, that number goes up rapidly. Give you an example quickly for a Melbourne home, 180 square meters. Sorry, we talk 14.4 kilowatts heating, and using the same numbers, we talk 14.5 kilowatts cooling, which is actually nicely balanced. Just to be clear, this is peak load, as I said before, and it does not mean that throughout the year we actually need more cooling. That's not the case in Melbourne. In a Victorian climate, it's always going to be a heating dominant house, no matter whether that number actually exceeds the heating number. Throughout the year, if we're talking kilowatt hours or megajoules or kilojoules, the heating load will be much greater than the cooling load, which varies from state to state, obviously, but in Victoria, that's how it'll be. Put a little asterisk here. The asterisk is just to say that ultimately the building's performance can only be assessed reliably with the help of plans and energy reports, which we'll delve into later. Thermal bridges, such as balconies, which have weak points, can cause or induce for the energy to escape a house. And ultimately what this means is that the flow return delta, so the flow into the building from the heat pump, return back to the heat pump, that delta will widen. The more energy escapes, the colder the water, the heated water will be that returns to the heat pump, which means that that Kelvin delta widens. Our system is designed for 5 to 7 degrees Celsius loss between flow and return, essentially. So what you'll find in our manuals is going to say something like outside temperature 7, water 35 into the slab, and a delta of 5 Kelvin at 1.5 cubic meters an hour, so 1,400 liters an hour. Now, what we'll do in the second module is we'll quickly compare that number and what that heat load would be to what the exact same calculation would result in if we had a delta of 10 Kelvin, for example. You see that that heat load will dramatically spike quickly. So final sentence maybe, and we won't cover all of that. That's probably more one for a later session today, which is components, heat pump components. We're designing the system up to the manifold. And based on that, the flow rate, etc., determines the buffer size, the pump size, and so on and so forth. We'll look at a couple more buffer sizing examples in module 2, but just know that we design a holistic system, and every component that we throw into the mix will be designed around the flow rates of our heat pumps, essentially, and accommodate for those flow rates. All right, so let's look at it, the nuts and bolts of it. If you have a quick peek on the left-hand side, the heat pump sizing graph here, you see that the gray line basically depicts your heat load. What does that mean? The heat load, as we said before, design temperature is the coldest point of the year. In Melbourne, that would likely be around 2 degrees. And up here, that's the heat load, essentially, which is 16 kilowatts in this example. So obviously, as it gets warmer outside, you'll see the outside temperature increases. That heat load will then accordingly drop down to 20. At 20 outside, the heat load for the house is going to be 0. That makes a lot of sense. So basically, if you look at the line, which, as I said, represents the heat load, you'll understand that the flatter this line is, the worse basically the heat load and the worse the house is performing, because flatter means, you know, at, let's say 25, you'd still have to heat, which is very unlikely, but get my point. And opposite, the steeper, the better, for the same reason. Let's say at 10 degrees, your house holds up well, does not need to be heated anymore. At 10 degrees, the heat load would be 0, then that's great. It means a very steep line here. The opposite on the opposite end, here, sorry, quickly going back, dual mode point is 4. In this case, that's the bivalence point, which means at this point, where's the dual point? It should be 4 here. Sorry, it's up here. It's a little small for me. So up here, the dual mode point being there's a teeny tiny bit left of the heat load that the compressor, which is covered by this red area, that's the compressor range of our heat pump, can no longer cover by itself. So there's a little bit here, which is going to be effectively maybe 1% throughout the year in terms of complete demand needed, that we cannot cover with the compressor. And at that point, we would need a second heat generator or a second heat source to kick in to help. That's hence the bivalence point. But this is still a very good design, hence the tick here. Opposite to that, on the flip side, we'll see if we have a much greater heat load, 24.5 in this case, and the same heat pump, you'll see that that bivalence point arrives or shows up much earlier, 9.6 degrees. And any temperature below 9.6 would accordingly need the help of an element or second heat source, which is a very great area here. Would not be a good design. In this case, there's a couple of things we could do about it, and we'll delve into that in a second. Lastly, as I said at the very beginning, we don't want to undersize, but also not oversize, because this area here, as you'll see, even though it's a very good design, is not going to be within the range of the compressor, which effectively means as soon as we arrive at 10 degrees outside, from 10 to 20 degrees, the heat pump could no longer just ramp down the inverter and run constantly, which is the most efficient way of doing it, but it would actually have to come on and off and on and off and on and off and sort of click its way down to deliver those smaller loads. All right, how are we going for time? Got a bit of time left. Okay, so same thing, different look, but just another example, I suppose. We've got the annual coverage achieved by the heat pump here. You'll see the design temperature is 14 degrees. We can deliver most of it with the heat pump 13 kilowatt heat demand down to -14. We're in Europe now, so it's different look, but same principle applies. And we have a geothermal pump. The output, we'll look into that as well. As I said, the output for a geothermal pump is constant, very flat lining essentially, no matter what the temperatures are. So effectively 99% of the demand throughout the year will be covered by the geothermal heat pump, and only 1% up here would not be able to be covered, and that's at very cold temperatures. I'm putting this one up because in comparison, if we look at an air sourced heat pump, you see that line is very different here, and that's because the output for air source differs. And by that, I mean, as it gets warmer, the output will get greater. It's not a flat line. And what that effectively means is that if we on the same job, we put an air source heat pump on, you see that 2 to 3% are not covered throughout the year, as opposed to the geothermal job before, which would have covered a lot more just because the output is more constant throughout the year, even during the cold temperatures. All right, I'm going to speed this up a little bit. Now, geothermal heat pumps, oftentimes, our systems at least, even though that's going to change soon, have a start-stop compressor, not the inverter range. What that means is if we had 100 kilowatt capacity, this is a big job down to -20. At the coldest time of the year, this compressor would just run 24 hours a day, perfectly fine, great design. If we approach the 0 degree point, again, European temperatures, that means the compressor only has to run 12 hours a day, and it can only click on and off and on and off in between, basically, because it can only deliver 100% or 0%, 100% or 0%, which towards the end means effectively the compressor clicks on and off quite a lot, and it's not the most efficient design. All right, opposite to that, inverter system. As I said before, we have a range. So if we look at maybe flow temperatures of water 55, the blue line, this is the maximum the compressor can deliver. And the dotted blue line is the minimum the compressor can deliver. You see at, let's say, 10 degrees, that would be 5 to 6 approximately that it can deliver while still operating, while the inverter ramps the compressor down and the compressor is constantly running, which is what we want to achieve for an efficient design. And it can go up to 16. So it's a relatively wide margin, which is good. Ideally, if that line, let's look at that one, intersects somewhere down here and covers, as I said, a large amount from 0 to -15 in Europe, that's a great design. We'll see here the maximum capacity of this particular example is met or hit at -12. And then because we can go down in this climate to -15, that effectively means there's a teeny tiny bit here again where that's the bivalence point here, and where we would need a second heat source to kick in and help with those last couple of degrees. Now we're drawing a few lines on here just to make that one once a little more clear again. Everything green here, especially everything within the compressor range, would be covered. Down to this point, it's still very much within the design, but obviously as soon as we drop out of the inverter range, it, as I said before, has to click on and off, but that's still fine, still all green. And then up here, this should be red. This should be your second heat source kicking in and helping with those couple hours a year where we actually go lower than -14 in that example. So that's a constant running point, as I said. Below, for a smaller heat load, it can no longer constantly run, but has to click on and off. And up here, that's our dual mode point, the bivalence point. Got a couple more examples just to hammer it home. In this example, we are talking a heat demand of 15 kilowatts down to 0 degrees, 0 degrees being the coldest time of the year in the UK. And we have a WPL 23, which is capable of exactly 15 kilowatts. And that's basically a perfect match, meaning 15 kilowatts at 0, we can achieve it. This is what we would call a monovalent design. Great, happy. On the flip side, again, we're talking another example, UK, 16 kilowatts down to -5. And we only have a WPL 18, which is a 12 kilowatt unit to contend with. That would mean 12 up here, down to 0. And then the rest down to -5, we could no longer cover using the heat pump itself. So in that point, we'd probably have an element kick in at the bivalence point of 0 and help out with that little bit here. There you go. All right, I'm hoping that's sort of clear. If not, chat me a few questions and we'll get into it later, but this should so far be relatively straightforward. All right, a couple other points. I touched on that before. The heat load is not to be confused with the annual heat demand total, which is unsuitable for sizing the heat generator. A 16 kilowatt heat load home means that approximately, and this is one of our tools that can calculate it, approximately we would expect 46,784 kilowatt hours per year demand for that 16 kilowatt heat load home. The 4-degree bivalence point, I think we've belabored that one a few times now. What's interesting here is that the 4 degrees is not necessarily suitable to determine whether or not we're dealing with a good design. It can be, but it's not always. 4 degrees might sound like that's relatively early for some climates. I mean, in the ACT or something, we can go down to -degrees. If we say 4 degrees is the bivalence point, that might shock some people and say, oh, what happens below 4? But I sort of wanted to make clear that even in this example, it's 99.9% covered. Heat pump coverage, heat demand is 99.9%. And that is because if we look over here, the outside temperature 4, this is actual climate data for the area, in this case for Melbourne. I don't know if you guys can read it, I hope you can. It basically says frequency of this temperature or colder. So 4 degrees or less than 4 degrees in this climate area is only 102 hours per year. It's not a lot. And that's why over the course of 3,311 running hours a year, those 100 hours are really not that much. So if we have 0.1% of the time where an element would have to kick in, that still makes it a very efficient design. There might be climate zones where that number, 102 hours a year, might be much, much, much greater. And in that case, it's important to understand that. And then 4 degrees would not be a good bivalence point for obvious reasons, because we want to cover at least, as I said, if we can cover 99%, that's great. But if all of a sudden the number is 70%, because we have much colder, much more, then it's no longer going to be a suitable heat pump. All right, have we covered everything here? Yes, let's move on to the next one. Another important consideration to factor in is flow temperatures, and that's also a horse we keep flogging, I suppose. Our heat pumps can only produce 65 degrees in flow temperature. Ideally, that means that radiator systems are designed for 60 degrees flow, just because we have a little bit of energy loss between the heat pump and the radiators. If you look at this line here, that sort of represents the 60-degree output that most of our heat pumps can deliver, you'll understand. And again, we're in Europe right now, so the temperatures are a little different, but it still applies because the building standards in Australia are, comparatively speaking, not as good. So just imagine the scale to be maybe -5 at the coldest, but the principle stands. You'll see that a 60-degree flow temperature can now deliver all the way down to whatever the coldest point in Australia would be. Whereas if we have a system, a radiator system that's designed for the blue curve, 75 degrees, it would only be able to, this is like the heat load curve essentially, it would only be able to deliver heat, a good amount of heat down to a certain point, maybe 5 degrees in Australia. And then as soon as we dip below 5, system would no longer be able to deliver the right amount of heat, not enough heat essentially. Okay, radiator systems used to be sized for 75, as I said. Today, most systems can do with much less, 60. It obviously means physically the radiators have to be sized accordingly as well. We need more fins, we need more surface area. Ideally 55 degrees to enable mono-mode operation. All right, how much time do we have? 10 minutes, okay. We'll quickly delve into geothermal heat pumps and sizing the source. Having said all of that, we have courses and seminars just for sizing the collectors, sizing geothermal sources. I believe that's on Thursday. So I encourage you guys to sign up for that one. We'll only superficially touch on this one briefly. Horizontal collectors, size of the area required for the geothermal collector depends on the refrigeration capacity of the heat pump and the heat storage properties of the ground. The required size of the geothermal collector is calculated subject to the prevailing ground conditions. What all of this basically means is that the area, the soil that the probes will be in, or the slinkies will be in, whichever system you choose, needs to be surveyed. It needs to be examined for the extraction rate, essentially, meaning the more humid or wet the soil is, the better, because of conductivity, essentially. And ideally, there's some groundwater or something involved, because that will increase the extraction rate. And if the more heat we can actually extract from the ground, the less collector material we will need. That's what it boils down to. Ground with groundwater is about as good as it gets, and that would mean 30 to 40 watts per square meter of horizontal collector area. So you see that dramatically would decrease the total amount of collector size compared to a dry sandy soil. It's probably 3 to 4 times the area size needed. And then just to give you a number, a typical 16 kilowatt install would approximately require 532 square meters of area, which is 9 times 100 meter traces. Or for probes, if we go vertical, 266 meter total, which could be split up into 3 probes. As I said, we'll do a little more on module 2, but we'll also have dedicated seminars or webinars for this topic later this week. Okay, gotta speed it up a little bit. Design, let's look at buffer tanks briefly. The main, or one of the big advantages of having a buffer in the system is, as I said before, the clicking on and off can be decreased or minimized because we're storing energy in the buffer, which then means we can release that energy throughout the day without the heat pump actually having to come on and off and on and off. So a little bit of efficiency will be added to the system there. De-icing and cold climate is an important one. We need to store some energy in the buffer tank because we have to de-ice, reverse cycle de-ice the system now and then as it gets colder. The energy can be stored in there. And it's actually required as well. We look at minimum water contents required in the system for that exact reason as well. We don't have to worry about the water content in the system if we have a buffer tank. So lots of points here. We won't go through all of them right now just to save a little bit of time, but there's a good case to be made for a buffer to be included in the system. Now we'll quickly look at 2 example system designs. One is a WPF16, a geothermal heat pump. If you look at this now, I'm hoping it'll make a bit more sense in a minute, because I will also show you what the wiring will look like, or what the wiring corresponds to. On here, if you can spot the heat pump, let me see if I have my pointer again. Heat pump is here. This is a WPF16, a geothermal heat pump. These would be our collectors. We have a heat pump manager here, the buffer tank, and then 2 circuits, meaning one here, one straight circuit and one mixed circuit, which could basically operate on a different lower temperature. For example, radiators here, in slab here. We have a buffer charging pump here and a couple of sensors, a flow sensor, forward flow sensor, a buffer tank sensor, an outside temperature sensor, a sensor here, as I said, because this is a mixed circuit which might operate on a different temperature and the system has to ensure that it does, and the source pump here. Now what that corresponds to is this, again, heat pump here. This is the WPM, the heat pump manager, and we'll have the sensors here. So 2.3, 2.4, sorry, are the pumps. Those are the circuit pumps. 2.6 is the buffer charging pump. And then a bunch of sensors, as we said before, essentially. What do we have? We have the buffer at 1.4, which is this guy here. Outside temperature at 1.3, this guy, and so on and so forth. All right, now we'll quickly look at domestic hot water and another system that would incorporate domestic hot water, and then we should get to the end of this one. Not to make it too much about system components in this example, but essentially we have a buffer cylinder, or multiple buffer cylinders, I should say. We've got domestic hot water cylinders, which are SPB tanks. I'm just going to deactivate the laser pointer, sorry. We've got an instantaneous water cylinder, which is a coil tank that has domestic hot water or potable water run through the coil. The buffer itself heats it up as it goes from the bottom to the top. And we have combination tanks, which essentially have a buffer tank at the bottom and the domestic hot water tank at the top. We'll only look at the standard coil tank domestic hot water SPB style in this module, and then we'll go into somewhat more advanced setups in the second module. So as you can see, the SPB has an inside coil, as I said. The potable water, it's a mains pressure tank, essentially. The potable water is on the outside here. It fills up the tank. The coil is used for hydronic heating water to run through and warm up or add energy to the potable water. Heat exchanger surface size is crucial. We'll look into that as well in module 2 a little more. But what I'm saying is we need 4, 5, 6 square meter coil surface area. That's important to actually transfer all the energy from the heating into the buffer tank, sorry, into the coil tank, into the domestic hot water tank. We prefer to do, if we do domestic hot water only jobs, we prefer to do on-off compressors and not inverter range compressors. And that's mostly because if we have an inverter, it'll often run at full hertz, full capacity, 120 hertz, for example, which isn't good for the lifespan of the compressor. Ideally, with an on-off compressor, that is not a problem. All right, we'll click through this a little quicker. As I said here, we have plenty of coil surface area from 3 up to 6.4 for the smaller SPB tanks. Maybe a quick example, if I said that before, 0.25 square meters are required per kilowatt. That's a rule of thumb. This is perfect for 14 kilowatt units, for example, these numbers. If we had less than that, and that's a common problem, is people like to have their own coil tanks, for example, for domestic hot water, and they have much smaller surfaces, like 1.5 square meters, for example, coil surface. If we connected that and use the rule of thumb, so we said 1.5 square meters divided by 0.25 square meters per kilowatt, that number would be 6 kilowatts, meaning we could only realistically transfer 6 kilowatts of heat into that tank. So it'd be wasteful to connect that to a 14 kilowatt unit, if that makes sense. Plus, we would not be able to get to those hot temperatures anyway in the tank. 50, 60 degrees might be out of reach. So that's the importance of having those coils large. All right, I'll try to speed up. Here's an example of a heat pump air sourced system with that SPB tank added. I'm going to activate my pointer again. That's the SPB tank added. What we're looking at here is the heat pump, excuse me, HMS Trent. HMS Trent, and we'll look into the HMS Trent in module 2 a little bit more. A buffer tank, and again, 2 circuits. What we can do here is we could do cooling for the first circuit. We could do in-slab cooling for the second. We'll get into that as well later. We cannot do pool heating, but we can realistically do normal heating, cooling, and domestic hot water. Again, this is the equivalent for the WPM and the wiring, the electrical diagram. You see two circuits here connected. You see the buffer charging pump connected here. You see the array of sensors. I'll quickly go back, but outside temperature sensor, top for cooling, bottom for heating, mostly 1.8 is a domestic hot water sensor. And then this second sensor here for the circuit, which might operate on a different temperature. Okay. Final note before we wrap this one up is on active cooling and passive cooling. And I was sort of alluding to that before when I said with this system, these two circuits would have different functionalities or capabilities when it comes to cooling. Question is maybe why is that? In this case, it's because we have a controller here, which has certain features like dew point monitoring, and the first circuit doesn't have that. Now, dew point monitoring we will need for in-slab cooling, and that's because we want to make sure that we do not undershoot that dew point for the slab, which would lead to condensation and potentially damage, corrosion, all these issues. So for the slab, we cannot run much colder than 15-degree water through it, and we need to monitor that constantly. So if a controller like that is installed, we can achieve it. If it's not, we could only do active cooling fan coil unit style, if that makes sense, which is the first circuit. So we could send much colder water through that system, through a cassette, for example, fan force cassette that then blows cold air into the place. Two different approaches, both have their pros and cons, and we explore them a little later. But essentially, that brings us to active passive cooling. And that's sort of the note that we'll end on. A couple of things here. Active and passive cooling, there's a lot of terminology around it, and sometimes it gets confusing when we talk surface cooling and passive cooling, which one is which. The easiest way to do it, or to keep them separate, in my opinion, is to talk active cooling, meaning the compressor of the heat pump is engaged, be that a air source or a geothermal heat pump, versus passive cooling, meaning the compressor is completely idle. That by definition means that a geothermal system can achieve passive cooling or can perform passive cooling, and an air source heat pump cannot. Because an air source heat pump, even when we do the surface cooling, which is a lower, or I should say a higher flow temperature, around, as I said, 15, 16 degrees, tepid sort of temperatures, it still needs to engage the compressor. Not as much, obviously, as cooling the water down to 5 degrees, but it still has to work. So active cooling breaks down into active cooling down to 5 and surface cooling, which is 15, 16 degrees, depending on the dew point in the building. Passive cooling, and the schematic here is for geothermal heat pumps. The air source schematic would look exactly the same. That's why we decided to not post it. The geothermal install would require a good amount of valving, up to 4 valves essentially. And again, we'll sort of get into the nuts and bolts of that in module 2. But we would use a couple of valves essentially to just swap in passive cooling, just swap the energy from the building envelope with the cooler energy in the soil. So these would just reverse flow direction, if that makes sense, in a passive state without the compressor being engaged. Passive cooling, sorry, that's actually this guy here. And then for the air source heat pumps, we would always need the compressor to come on and cool the water down to a certain temperature, reverse cycle cool it. As I said, 15 degrees for passive. And then if we have fan coils in the system at home, we could go down all the way to 5 degrees. That's potentially possible with the air source as well as geothermal heat pump system. All right, that's probably a lot. We'll stop here. Little teaser of what's to come in the 10 a.m. module. We will further delve into heat loads and some advanced ways of calculating them, not just those rules of thumb. We will look at sizing buffer tanks and when they might be dispensable or expendable when we don't have to use them. We'll look at sizing domestic hot water a little more. We will look at those combi tanks that are only very briefly grazed. We will look at cascading systems and the dual operation that I also briefly introduced to you, and what sort of second heat sources can be introduced into the system and how that would be done. We'll do a little more about active cooling and passive cooling and solar thermal as well as pool operation in the second one. Okay, now I think it's, yeah, I've probably taken up enough time for the first one. I'll briefly check my chat to see if there's a few questions, which is the case. So we'll work through those. If you have follow-up questions, or if it's not satisfactory, what I'm going to tell you, maybe quickly shoot me another message, and we still have 10 minutes roughly to sort that out. And as I said, in the second module, after I've done that one, it shouldn't take much more than half an hour either, to be honest. I'm more than happy to unmute you guys if you want to have a, not face-to-face, but an actual discussion to clarify a few points. All right, let's start in chronological order. Do you factor in air tightness when estimating heating cooling loads, or just assume a 15 square meter? All right, so the question is, do you factor in air tightness when estimating heating and cooling loads, or just assume 15 square meters or cubic meters for a very leaky building? We would factor it in. Again, it's something for module 2 maybe, but there's a couple, with the rule of thumb approach, we would probably not factor in air tightness. We just look at, as I said, a couple of variables and say, look, this is going to be 70, 80, 90, 100 watts per square meter, and the same for cooling. If we have more information, like air tightness, blower door tests, all types of performance reports for buildings, then we will use different tools, which also include, is this place windy? Is it in a sheltered location? Which sort of, I guess, feeds into air tightness, and that then adds a factor of, or a mathematical factor to the equation, which will inflate the heat load or cooling load for sure. So long story short, it probably depends on the model that we use, and that is contingent on how much information we have. Hope that's good enough, James. Next question. For the insulation of piping to avoid heat losses, what is the usual insulation thickness? That's a bit of a how long is piece of string type of question. It depends on the pipe material itself and the length of the pipe and the diameter of the pipe. The greater the diameter, the less the heat loss, obviously, because the flow speed is going to be quicker. 30, 40, 50 mil, it really depends. It's tough one for me to answer off the top of my head. Obviously, the more, the better. And we can calculate those losses as well in kilowatt hours throughout the year, and then say to a customer, compare two different insulation levels and say, hey, put the bigger one in and it'll save you 600 kilowatt hours a year, which you can then put a price tag on. And that's obviously going to be attractive. Next question. These base values, 30, 40, 80, etc. per square meter, where are they derived from? There was this example of 180 square meters times 80 watts. Derived from what source, or just experience? A little bit of both. We get those values from, well, we used to get them from Germany. As I said, they've changed quite a bit. So in Australia, it's mostly experience, I would say. In Germany, we've got a pretty good catalog of what exactly translates to what. Here, it's mostly experience at this point. And as I said, it's the rule of thumb. So we have tools to actually back that experience up. If we have, oftentimes, if we have the information available, like a performance report, we'll do a rule of thumb first, and then we'll punch all that information into a more detailed, better analysis tool. And we oftentimes see that it comes out very much in the same ballpark. It's definitely conservative, meaning that if we have more information, the actual number that we get is probably going to be a bit better, a little more charitable, if that makes sense. So this is sort of worst case what we do. When we say 80 watts, it's a good chance it's actually 70 watts or 75 watts, but we want to cover our basis, if that makes sense. A little more on that in module 2 as well. Hope that's going to be satisfactory. Okay, guys, if there's not any more questions, I'll see if I can make sure you haven't raised your hand. Still getting the hang of Zoom. I think that's it, guys. I'll give you 5 more minutes. I'll just hang around here. And if everyone is happy, awesome. I would see you again, if you like, at 10 a.m. And we'll do the same all over again. Thanks, guys. Thanks very much. I'll stick around for 5 minutes, just in case. Otherwise, appreciate you taking out your time this morning. I'll see you soon. just a quick one, guys. I'll duck out now. What I should have maybe made clear is that you need to join the next seminar at 10 by clicking on the separate link that should have been sent out to you via mail. So I'll shut this one down and then I'll launch the next one in about 5 to 10 minutes. And I'll see you then. Cheers. See you.